Good morning, ladies and gentlemen, and welcome to the Applied Physics Laboratory for what I hope will be a fascinating day for all of us as we follow the progress of the Near Asteroid Rendezvous encounter with 433 Eros. I would also like to welcome those of you watching this on TV and hope that you will be able to share the sense of the excitement here at the laboratory. For those of you who don't know me, I'm Tom Kremidis, head of the Space Department here at the Applied Physics Lab, and it has been my privilege to work at APL for more than 31 years, and I've served as head of the Space Department for the past 9 years. We're expecting quite a few VIPs today, among them NASA's administrator, Mr. Dan Goldin, whom I'm sure this audience is very familiar with. We're also expecting the Honorable Senator Barbara Mikulski and the Honorable Senator Paul Sarbanes, both representing Maryland in the United States Senate. We have quite a lineup today of experts who will speak to you about the asteroid in general, the NEAR spacecraft and its instruments, the overall mission of NEAR, and the images that we have been receiving since NEAR's flyby of Eros in December 1998. We will end the morning with live coverage from the Mission Operations Center, or MOC as we call it, to verify that NEAR has gone into orbit around Eros. Now, to get things started, I would like to introduce to you Dr. Richard Rocca, APL's new director. Dr. Rocca recently joined APL, and we're delighted to have him with us. Dr. Rocca spent many years with Bell Laboratories, most recently as vice president of AT&T Laboratories. Without further ado, I would like to ask Dr. Rocca to the podium. Dr. Rocca.
Thank you, Tom. On behalf of all the members of the Applied Physics Laboratory of Johns Hopkins University, and on behalf of the larger Johns Hopkins community, its President Bill Brody and the Board of Trustees, it's my privilege to welcome all of you to this historic occasion. APL has been in the business of building satellites, especially small satellites, for over 40 years, beginning in 1958 with the invention of Transit, the world's first satellite navigation system. For decades, we've had the privilege to work with NASA and have been proud partners with the NASA centers, including the Goddard Space Flight Center and the Jet Propulsion Laboratory at Caltech. It is indeed a privilege for the Johns Hopkins Applied Physics Laboratory that we were selected by NASA to implement NEAR, the first discovery mission, and to introduce the management principles so ably advocated by the NASA administrator, Dan Goldin, into the planetary program. We're all here today to witness the success of this approach to planetary exploration. The NEAR mission, together with the success last year of the Far Ultraviolet Spectroscopic Explorer, FUSE, also implemented at Johns Hopkins, has clearly demonstrated that the broadening of NASA's program through partnerships with academic institutions and university laboratories is an outstanding success. And it is gratifying to see, as best as we can tell from the recently submitted budget, that NASA plans to expand these partnerships. Again, I would like to welcome all of you to the Applied Physics Laboratory and hope that you are as excited as we are following the events of today. Tom?
Thank you, Rich. Before we move on, I would like to share with you a little history about the NEAR mission. The quote, better, faster, cheaper, unquote, paradigm was established as the cornerstone of NASA's discovery program in the early 90s. This has been a very successful concept, and we cherish the opportunity to be the first ones to implement this in the interplanetary program. because, generally speaking, there was recognition in the science community that smaller spacecraft was the way to go. About 4 years ago, in this very room, our late colleague and friend of many of us, Carl Sagan, had this to say about the coming of the new era. As you can see, he talked about the making spacecraft small, light, and elegant, while at the same time sacrificing little in the way of scientific productivity. And that's a very key point. And he recognized, of course, that Near is the first. Carl Sagan had recognized the historic step that Near was attempting in planetary exploration. In keeping with that concept, I would like to show you the dollar amounts that the Near mission costs came to. First of all, note that there was a cost cap for launch plus 30 days of $165 million that NASA had established. And our original estimate for the spacecraft was about $125 million. However, when we closed the books after launch plus 30 days, the actual cost ended up being $117 million. And the point to note here is that it was essentially $48 million below the cap that was established by the agency. Pardon me. This I meant on the overall program. The launch support and tracking was 44.6. And the mission operations and science analysis is estimated for 5 years, because we're on the 4th year now, at 54.6. So if you aggregate everything, the total mission cost was 216.2. So this, as things turned out, was the cost, and the Near program was certainly cheaper. The spacecraft was completed in 27 months from start, and that, I believe, makes it faster. And above all, it was most assuredly better. And I hope you will see this as today's events progress. And now I would like to introduce Mr. Tom Coughlin, the Near project manager, who will be your MC for the remainder of the morning. Mr. Coughlin has managed Near since its implementation, and it's also now programs manager for the space department at APL. He has been the maestro for this team, and he has brought not only great technical skill, but hardcore discipline, but also with much understanding, compassion, and a great sense of humor. And in terms of the latter, don't believe him if he claims that he lost his hair because of Near. Actually, he didn't have much hair when he started. Tom?
Good morning. At about 10:33 this morning, thrusters on the Near spacecraft will fire for approximately 1 minute. This will alter the spacecraft's velocity by 10 meters per second. When this maneuver is completed, we will be captured by the extremely small gravitational influence of the Manhattan-sized asteroid 433 Eros. When that is successfully accomplished, Near will be the first spacecraft to orbit a small body. Before we go over to the Mission Ops Center at 10:30, as Tom said, we'd like to provide you with a little background so that you can be more familiar with our mission. We're going to have a brief talk on asteroids, our final destination for today. We'll also talk to you about the instruments we're carrying aboard and how we will use them during our year in orbit around the asteroid. We then will have an overview of the spacecraft and how it operates, and then just before going over to Mission Ops, which is located here at APL, we will give you the latest images that we've taken on our approach to the asteroid. At 10:30, we will go over to Mission Ops, and about 10:47, we'll get our first data back from the spacecraft. A few minutes after 11, our engineering team will have had time to look at this data, and about 11:05, we believe we'll have adequate data to make a statement that we are in orbit. So let us get started this morning with a brief video, 11-minute video, that'll give you a little background on the Near mission. Thank you.
The journey to orbit an asteroid continues. Launched in February 1996 from Cape Canaveral, Florida, the Near Earth Asteroid Rendezvous, or NEAR, spacecraft will arrive early in the year 2000 at the asteroid Eros, the smallest solar system body to be orbited by a spacecraft. For up to a year, the trailblazing NEAR will probe the mysteries of asteroid composition, seeking clues to the origin and evolution of our solar system. NEAR is the first mission in NASA's Discovery program for lower-cost, more frequent planetary exploration. The mission is conducted for NASA by the Johns Hopkins University Applied Physics Laboratory in Laurel, Maryland, in partnership with a scientific team which includes Cornell University, the Jet Propulsion Laboratory, MIT, and the University of Maryland, among other institutions. NEAR was delivered to the launch pad in just 26 months from the award of New Start funding in December 1993. The end-to-end development process included computer-aided design, mechanical fabrication, spacecraft electronics, component tests, integration of key systems, and simulation of launch and space environments. NEAR's state-of-the-art instruments were chosen to maximize science return for the dollar. The instruments include a multispectral imager, X-ray and gamma-ray spectrometers, near-infrared spectrograph, laser rangefinder, and magnetometer. The completed NEAR spacecraft underwent environmental testing in fall 1995 at NASA's Goddard Space Flight Center in Greenbelt, Maryland. In early December 1995, NEAR was flown to Cape Canaveral Air Station in Florida for processing in facilities at the air station and at Kennedy Space Center. Preparations included mating with the third stage booster and final integration at Pad 17B for launch on the McDonnell Douglas Delta II rocket, a medium expendable launch vehicle now built by Boeing. February 17, 1996. The 1,800-pound NEAR spacecraft was poised atop the fully fueled Delta II.
16, 15, stopping, go 14, 13, 12.
T-minus 11, 10, 9, 8, 7, 6, 5, 4, 3, 2. We have engine started. We have ignition. We have liftoff of the Delta rocket carrying the NEAR spacecraft bound for the asteroid Eros.
We've ignited the other 3 solids, and all 6 of the first set are off. Here we have solid motor burnout, again very symmetrical. And we have solid motor jettison. All 3 of them came off cleanly. Attitude disturbances almost non-existent.
29 minutes into flight, the third stage booster separated after thrusting Near out of a brief parking orbit and free of Earth's gravitational pull. The spacecraft, designed to be simple and reliable, has just one deployable system, 4-foot by 6-foot solar panels that began powering Near as soon as the spacecraft exited Earth's shadow. Near's 35-month, 1.3 billion-mile journey to Eros is not a direct flight. En route to a deep space maneuver, Near passed within 750 miles of another asteroid in June 1997, the collision-battered 33-mile diameter Matilda, located in the main asteroid belt 186 million miles from the Sun. The flyby confirmed to scientists that C-type carbon-rich minor planets like Matilda are pristine examples of the primitive building blocks that constitute the larger planets. The 25-minute bonus flyby yielded the first Discovery mission data and images and was a preview for Near's rendezvous with the asteroid Eros in February 2000. To reach the distant Eros, the spacecraft received an energy boost by swinging out to nearly 200 million miles from the Sun, where a deep space maneuver in July 1997 with the spacecraft's powerful main thruster sent Near back towards home for a close encounter with Earth. In late January 1998, Near swooped in over the Hawaiian Islands and Asia, bringing it to within 335 miles above the Middle East, a swing-by which accelerated the spacecraft to over 29,000 miles an hour. With its reflective solar panels aimed at Earth, the Near mission operations team gently rocked the spacecraft to flash sunlight down to major cities across the United States, giving sky watchers the first ever unaided sighting of an interplanetary spacecraft. In addition to this sun-glint maneuver, scientists had another opportunity to perform calibration tests on Near's 6 instruments during the Earth swing-by. A series of photographs by the spacecraft's multispectral imager, designed to help calibrate the imaging instruments aboard Near, formed a motion picture portrait of the eastern and southern hemispheres during Near's sojourn to Earth. Using Earth's gravity as a slingshot, the spacecraft swung away from Earth and decelerated to 15,000 miles an hour, with its trajectory angle bent nearly 11 degrees out of the ecliptic to match Eros's orbital plane. For 12 months following the gravity assist, Near closes in on the asteroid, communicating with Earth through NASA's Deep Space Network. The spacecraft is commanded round the clock from an on-site control center at APL, where mission operations and science team members monitor its critical systems and direct Near performance. On December 23, 1998, Near observed 433 Eros from a distance of approximately 2,375 miles after an aborted main engine firing postponed the spacecraft's orbit insertion around the asteroid. The spacecraft's multispectral imager, infrared spectrometer, and radio science experiment recorded valuable images and data as a prelude to a February 2000 rendezvous with Eros. Data generated during the flyby revealed the 21-mile-long by 8-mile-wide asteroid to have a density similar to that of the Earth's crust. Variations in surface color and reflected light are evidence of diverse surface composition, including high concentration of silicate minerals and metal. With a prominent ridge, fewer and smaller craters, and high density, scientists suggest that Eros is a relatively young and homogeneous asteroid, rather than an aggregation of rubble as observed on Matilda. Unlike the millions of main belt asteroids which orbit the Sun in a vast donut-shaped ring between Mars and Jupiter, Eros, first discovered in 1898, is one of the less abundant near-Earth asteroids, thought to be dead comets or fragments jarred from the main belt by asteroid collisions. Asteroids have struck our planet in the past. 65 million years ago, the impact of a 6-mile wide body may have caused mass extinctions on Earth. Eros, one of the largest and best observed of the Earth approachers, orbits the Sun in 21 months and passes no closer to Earth than 13 million miles. With fundamental information gained from the December 1998 Eros flyby, Near will initially enter a 600 by 250 mile elliptical orbit around the asteroid, using its camera and other instruments to refine the asteroid's dimensions and mass. The spacecraft is then carefully maneuvered into a 250 by 125 mile radius elliptical orbit. Over a period of months, that orbit is tightened to 22 miles. The closest Near gets to the Eros surface during the year-long rendezvous is approximately 9 miles. Near's instruments are designed to determine surface composition and physical properties, and to photograph surface features like craters as small as 3 feet in diameter. A century after its discovery, scientists have begun to unravel the mysteries of Eros and are anticipating a more comprehensive study during Near's year-long rendezvous. Earth and the other inner planets have changed dramatically over time, and traces of their birth 4.5 billion years ago have been erased or obscured. But asteroids may preserve intact, primitive material from those earliest days of solar system genesis. Near, during its historic rendezvous at Eros, promises our first long-term, close-up look at an asteroid, and an unprecedented opportunity to answer fundamental questions about the solar system and the universe, educating and preparing future generations for the world of tomorrow. The Near Earth Asteroid Rendezvous, the first mission in NASA's Discovery program. The journey to visit an asteroid continues.
Okay, our first speaker this morning is a member of our science team. Our science team was selected competitively by NASA in 1994. Dr. Lucy McFadden from the University of Maryland is a member of our imaging and infrared spectrometry team. So Dr. McFadden will talk to us this morning on asteroids. Thank you, Lucy.
Good morning. Thank you for joining us today as we continue our discovery mission to asteroid Eros. I'd like to set the stage, but realize that the end of our story won't be written before the year is out. This is not only because our orbital mission will be returning scientific data for the next year, but also because the path to discovery is circuitous and a process that involves testing observations against expectations, and that path often goes in fits and starts. We will be looking at our data. We will be analyzing our results. We will be critiquing each other's thoughts, going back and reanalyzing and reformulating our theory, all within the framework of physics, chemistry, and the measurement uncertainties of the instruments on board the spacecraft, which are inevitable. Here is the table of contents for the story so far. We'll start looking back in time, long, long ago. I'll give our summary of our favorite asteroid, though others will do so more thoroughly. We will extend our scientific knowledge of Eros and connect it to asteroid samples on Earth, and you'll hear more about that later. And we also expect to learn something about Eros that will help us understand the crater forming process for objects that sometimes hit Earth. Another important connection is that to the tens of thousands of asteroids that orbit the sun in the main asteroid belt. Now, many people ask me why I do this, especially my relatives, and I know my science team members are asked the same. My closing comments won't explain it all, but I hope they will help a little. We are the third planet from the sun in what we call the solar system with 2 capital S's. The 9 planets orbiting the sun in elliptical orbits comprise the majority of the solar system's condensed matter today. Eros is currently located between Mars and Earth in a grossly exaggerated size here, though it does travel beyond Mars toward Jupiter into the main belt. Now, if we rotate our view 90 degrees to a point above the planets, looking down on them, you will see the tens of thousands of asteroids of the main belt. Eros is a member of the subclass of asteroids called the Amors, which carry them out to the main belt and across the path of Mars and toward Earth. But Eros does not cross Earth's orbit, and it won't do so within the next 10 or 20 million years. So I really don't think we have anything to worry about, because our calculations which provide that number have been done by accounting for the gravitational perturbations of all the planets in the solar system over time. Now, Eros was the first asteroid found of this family. It's one of the larger of the Amors. It was discovered in 1898, as the video recounted to you, and we've been seeking Eros for over 100 years. Now, bear in mind that as we study an asteroid, we are looking back in time. We're looking back to the early stages of the solar nebula, and as you can see, I've represented in this artist's impression, which is a painting done by our colleague William Hartman of Planetary Science Institute. This is the gas. We are looking at the gas and dust rotating in the solar nebula around the protosun. That's the forming sun, which is the precursor of the solar system of today. The fragments of dust and gas collided and stuck together, growing into kilometer-sized objects within the first 500,000 years of the solar system. That's the equivalent of about 1 to 2 hours of a human lifetime. So let's give the asteroids a few more minutes to form, and keep in mind that the tug of gravitational forces between the sun and Jupiter prevented these planetesimals from growing to full-sized planets. Hence, the main belt asteroid exists today, and when we study an asteroid, we are looking back in time 4.5 billion years ago. So here's one of many images that you'll see of Eros over the next year. I particularly chose one from a few days ago so that you could see our sense of eagerness to look more closely, to get a better view and more detailed images of the surface of this asteroid named after the god of love. You will have to wait through the upcoming year to see the maps that we will produce. We will be making morphology maps, topography maps, magnetic field. We'll show the magnetic field and the interaction of Eros with the solar wind. We'll have maps of the elemental and mineralogical abundances. And be patient with us, and you'll see a world of long, long ago, from the time before the planets formed. The science team is often asked what Eros will tell us about the asteroids that might hit the Earth or have done so in the past. I first answer that if any specific asteroid is on a collision course with Earth, its mass times the square of its velocity will determine how much damage is done to Earth, for that is the energy of any object in motion. But in our analysis, we will be able to model the interior structure of Eros and use that information to better understand the processes by which craters formed on Earth from fragments that are mostly smaller than Eros. But with this knowledge of the interior structure, whether it is cemented rock or extremely porous material, it will help to determine what it would take to modify the course of any asteroid that might be on a collision course with Earth. Note that most of the large craters on Earth, such as this one at Meteor Crater in Arizona, were formed millions of years ago. There is a very real probability, but a very small one, that an asteroid of significant energy will strike the surface of the Earth in the future. But that probability is small, and we cannot predict the time and if at all it will happen. In short, I don't lose sleep about asteroid collisions on a daily basis, but we do have to pay attention, and we will contribute our knowledge of asteroid structure to the effort to mitigate any future hazards. After our year of analyzing our return data from the Near spacecraft, we will have abundant knowledge of Eros, and Eros will become the standard to which all telescopic observations will be compared. We expect to be closer to filling in our puzzle of the formation of the solar system before the planets formed. Now, our journey to Eros began with its discovery in 1898. We've followed its path in the solar system as a point of light, even using Eros to determine the distance between the Earth and the Sun prior to the availability of radar in the middle of the last century. We've studied Eros from afar in 1973 with telescopes around the world when Eros came particularly close to Earth. We launched our spacecraft in 1996, and we attempted to conduct our mission last year, but we were foiled by the fates of unanticipated physical conditions. You can imagine that the science team feels a little bit like Psyche, a mortal of great beauty who was banished by a jealous goddess, Venus. She foolishly asked her son, Eros, to do away with Psyche, but he fell in love with her. Not wanting to get into trouble with his mother, he refused to let Psyche cast her eyes upon him. Psyche, however, was deeply in love with her lover who came to her only by the dark of night. She was driven by curiosity, driven to see the man she loved. She cast a light upon Eros, who awoke and fled, leaving Psyche to spend another dozen years in search of her lover. Let's hope that the gods are with us today and will give us the view of our love that we've worked so hard to see. Thank you.
For those of you that are familiar with the Discovery program, you're aware that they operate in the principal investigator mode. That is, the scientist, who we do these missions for, has ultimate responsibility and authority. The first two missions in Discovery didn't start out that way. Mars Pathfinder and Near have what we call a project scientist. Our project scientist is from here at APL. It's Dr. Andrew Chang, and he will talk to us about the instruments that we're taking to Eros and how we intend to use them over the next year. Andy?
Thank you very much. Well, Near is all about asteroids, as you just heard, and Near will give us our first chance to get a really good look at an asteroid. In the past, we have had several missions that caught fleeting glimpses of asteroids by zooming by at speeds of anywhere from 20 to 30,000 miles per hour. But Near, in fact, will go into orbit around Eros, and we'll be studying Eros for a year and at speeds more like 5 miles an hour. So we'll get a much better look, and we're going to hopefully answer some big questions about what the asteroids actually are, and hopefully we'll be able to read the story that asteroids can tell us about the very beginnings of our solar system. Now, some asteroids are, in fact, older than the Earth. They preserve materials that have scarcely changed since the very beginnings of our solar system 4.5 billion years ago. Now, one big question we have is whether Eros is one of those. We don't even know that for sure. Now, as you can see in this graphic, the 3 asteroids that are shown are Matilda, our friend that we flew by, Near flew by in June 1997. That's the largest asteroid on the left. And in the corner, the lower right, there's a comparatively little asteroid called Gaspra. Gaspra is an example of the other type of asteroid, which is not as primitive, but which is in fact a fragment of a planet that once formed, but was subsequently broken up by a disastrous collision with another asteroid. And the main consequence of being once part of a planet is that by planet we mean an object that was big enough to trap heat to the extent that it melted on the inside. And when it melts, the different liquids can separate out in the same way that oil and water will separate in your salad. So if an object is big enough to sustain this type of melting and separation, why then it's undergoing the process that distinguishes it as a planet as opposed to a small body, by which we mean the objects, the asteroids and the comets. The comets are the small bodies that have ice on them, so they can make the beautiful tails that we see in the sky composed of gas and dust. The asteroids are the much more numerous small bodies that don't have enough ice to do that. They're just rocky objects. And of course, in this graphic, in the upper right corner, you see our old friend Eros, and all three of the asteroids were shown to scale in that image. So Eros is between the size of Matilda and Gaspra. However, we should also bear in mind Matilda is actually a much darker asteroid than the other two. It's almost black. In fact, if we had them as all three asteroids shown to the correct relative brightness, Matilda would be almost invisible. Now, why do we ask these questions? Why do we think we know something about the early solar system? Well, most of what we really know about the early solar system, we know because we study meteorites. Now, the meteorites are actually rocks that fall to Earth directly from outer space. So, what the meteorites are, mostly, are pieces of asteroids. Now, there are some meteorites that are also a small number of meteorites that come to us directly from planets, Mars in particular. There are also a very small number of meteorites that come from the moon, but almost all of the meteorites, we believe, are pieces of asteroids. And by studying the meteorites, that's how we know when the solar system formed. That's how we know the age of the solar system. That's how we know, in many cases, the kinds of bodies that existed very early in the solar system. We can tell you a lot about what we call parent bodies, the objects on which the meteorites form. We can tell you their sizes, much about their history. We can tell you all kinds of things, but maybe the most important thing we cannot tell you because we don't know. The most important thing we don't know about the meteorite parent bodies is their identities. We can't tell you which objects produced which type of meteorites. So anyhow, because we have meteorites that look like, some of them look like they've been scarcely altered since the very beginnings of the solar system, some have been heated to greater or lesser extent, some are produced by an object on which there was extensive melting and separation of different constituents. That's why we think all these different types of asteroids must be out there in the solar system. But we don't know which asteroids are which of these different types of meteorites. And one of the big questions we want to answer on NEAR is the connection. We want to make the connection. Is Eros, well, what type of asteroid is Eros? And the idea is we're going to be measuring the composition of Eros, and we're going to try to match that composition with the compositions you measure of the meteorites. And we may or may not be able to make a match, but if we can, we're going to have learned something really very important. Now, I have on the table next to me a really incredible collection of real meteorites. In fact, I am thrilled just to be this close to some of them. I never thought that would happen. The first two that are closest to me are examples of the very primitive kinds of materials that have been scarcely altered since before there was an Earth. They're called ordinary chondrites. And Eros, if it is in fact one of the asteroids that formed before the Earth, could have that kind of material on it. Okay? I should mention all of these samples are polished specimens. They don't actually look like that if you find them on the ground. Okay? They look much better. And they also look different. They obviously look different to the naked eye now. That's because they've been sliced and polished. As rocks, they're all kind of dark rocks, and that's exactly the problem. If you look at them if we look at an asteroid that could be made up of any of these through a telescope, it's awful hard to tell the difference between them. And that's why, even though there's a lot of telescopic observations of lots of asteroids, we still don't agree which asteroids are made up of which of these things. Okay, so the second group of 4 meteorites is, there are examples of what would happen if you had partial melting or incomplete separation of the liquids that formed from the melt. And these meteorites are especially rare, and I really never thought that I would have them within arm's length here. They're in fact so rare that no one should touch them without gloves. They will be here on the table for the whole day. They are from the Smithsonian Institute, and the curator of the National Meteorite Collection at the Smithsonian is with us. He's Dr. Timothy McCoy. He is a member of the Near Science team, and he will be here and available for people who want to ask him questions. Okay. The final group, farthest away from me, contains a bunch of meteorites that are samples of objects that did in fact go complete melting and separation, and the very beautiful specimens, the long elongated one on the right is an example of an iron, which is the kind of material that you might expect to find at the very center of a planet, like the center of our own Earth. It's mostly iron nickel. And the smaller meteorite in the front row on the left is an example of a basaltic kind of rock that would be found on the crust of a planet. The one in the back is something that is also a very curious meteorite that would be, again, from very deep down in a planet sort of near the boundary between the core and the mantle of a planet. So all of those, we believe, are pieces of planets that aren't in the solar system anymore because they have been broken to pieces. Now, what we're going to do, of course, is we have a very specialized set of instruments on the Near spacecraft to be able to try to tell the difference between all of these different types of materials. We cannot do that from the Earth. We have no way to do that. We have to bring these instruments up close to the asteroid and use them for a year in orbit around Eros to be able to say something about which types of rocks we will find on Eros. Okay. The Near payload, the principal instrument that we will be using to make the distinctions between the different types of rocks that we might be found are shown in this graphic. On the lower right, we show the X-ray and gamma ray spectrometer. What that does is it measures the elements that are found in the rocks. And the reason we can see that a rock has been melted and the elements have separated out is it leaves signatures, because if the irons melt and fall to the center of a planet and you have a sample from the center of the planet, well, you're going to see a lot of iron there, and you would see less if the rock is from the outer part of a planet. And if you have a very primitive composition, well, the iron would still be mixed in, so you have an intermediate amount. And so that's basically the idea behind trying to distinguish. You, of course, measure several elements, and by measuring several of the elements, you'll be able to make the distinction. We'll be able to say, maybe later this summer, whether Eros is an asteroid that's been scarcely altered since before the Earth. Okay. The other instrument that we will be using to look at the composition of the asteroid is the infrared spectrometer. I'm sorry, that's not here. Okay, let me talk about the other two instruments on this slide. The camera, which will be the star of the show for the rest of the day, is the top. This is a CCD camera. It's very similar to the video camera and the digital camera that you probably have in your home. And the magnetometer is shown on the lower right. It's what we use to measure the magnetic field. The magnetic field is another key indicator of whether there's been extensive heating and melting of the body. So if, in fact, Eros was once part of a planet, it could easily have picked up a significant magnetic field then. The remaining instruments are now the infrared spectrometer, which is used, that's in the lower right, we use that to distinguish the minerals that are present on the surface of the asteroid. On the top is a laser rangefinder, which is what we will use to make topographical maps. Just like the topographical maps that you use when you go hiking, you want to know how high you are and where the mountains are and where the valleys are. That's what we'll be doing with a laser rangefinder. And the other experiment, which is not a separate instrument, is the radio science experiment, and that is from radio tracking of the spacecraft. We're going to look at, and we're going to infer the gravity field of the asteroid and use that to see if, in fact, the asteroid has a uniform structure. Are there higher density and lower density regions within it, possibly different, possibly if Eros was, in fact, a agglomeration or a collection of different types of material, then you might very well find that kind of variation in the structure of the asteroid. Okay, the last slide I have here is a set of very useful websites. I'm just going to leave it up for a few minutes for people who would like to find out more about asteroids or about the collision hazard, because lately people have become very interested. Asteroids do hit the Earth. Throughout the history of the solar system, that has happened. It will happen again. And finally, notice that some of the best, in my opinion, some of the best websites available are in fact European. The bottom two are both in Europe, and they are very complete and wonderful websites.
Our next speaker was the lead engineer on our engineering development team, which Tom Kermit just said we got the spacecraft ready in 26 months. He led that team, but I guess he got bored, and he decided also to take up another job, and that was to head up our autonomy system. Deep space missions need to have fail-safe algorithms on board the spacecraft, as the time it takes to get a signal to it, at least on our mission, could be up to 20-25 minutes. Unfortunately, we've got to test Andy's autonomy system. It's protected us. It protected us 13 months ago, or we wouldn't all be here today. So I'd like to introduce Mr. Andy Santo, who is going to talk to us about how the spacecraft operates.
Okay, thank you, Tom. I'm very excited about today's activities. I'm very proud of the spacecraft that about 100 to 150 engineers and scientists here at APL put together. That spacecraft, the design team started in late 1993, and we went along to get to a February 1996 launch. Here you'll see the first slide that I have, and it's the center of the spacecraft, and it's the propulsion system. Now you'll see surrounded about the mid-band of that Earth are actually 3 tanks, and there's 2 tanks, one above the center of the spacecraft and one below the center of the spacecraft. You'll see a large thruster sticking out the side of the spacecraft, and you can notice that the thruster actually has burn marks on it, because like good consumers, we actually fired this engine before we purchased it. Now on the top of the spacecraft, right above the large engine, you can see smaller thrusters. Those thrusters are part of the thruster set that will be used in today's burn. Similarly, at the bottom of the spacecraft along the corner, you can see another single thruster. That is another one of the thrusters that'll be used. Now surrounding the spacecraft, you'll see a big aluminum structure, including aluminum top deck and bottom deck. Those elements are on there simply to hold the propulsion system elements. They actually are not part of the spacecraft. On this slide, you'll see our imager. It's about as big as a bread box and weighs about 10 pounds. On the front of the imager, you'll see a cover, and that cover has a transparent cap on it. We had this cap in case, for some reason, the cap would not deploy, we could still see through the cover. Fortunately, several months after launch, we did deploy that cover. It is open, and the imager is just working great. On this slide, you'll see a mock-up of the spacecraft and actually two flight antennas. The large antenna, which we call the high-gain antenna, and then there's a smaller sort of white rectangular antenna on the side of that. We call that a medium-gain antenna. Now, the larger the antenna is, the larger the area, the more that energy gets focused. So for our large antenna, that energy gets focused into about a 1-degree beam. And that's equivalent to, say, if you were looking through a straw, you would get about that same field of view. Now, using our high-gain antenna, we can downlink images approximately 1 per minute. So today, when you see images, or actually when you see movies, those movies are constructed by a series of images put together, and these images are usually separated by minutes or even tens of minutes. Now, we had a 3-year cruise phase, and then we did a burn abort, and then had another year cruise phase. So we went through 4 years up to now, and during that period, we talked with the spacecraft about 3 times a week. Each time, we had a duration pass of about 8 hours. Now, what do I mean when I say we talk to the spacecraft? Well, very similar to how you have a VCR at home and you point to the VCR and send commands like change the channel or increase the volume or decrease the volume, we send commands to the spacecraft. And those commands could be take an image, it could be point at Eros, another command may be point at the Earth and start sending data back. So we build up these series or sequences of commands. Now again, going back to the VCR, you can program your VCR to start recording at a certain time and say end at a certain time. Well, we program all the commands on our spacecraft ahead of time. And each of these commands on the spacecraft have an associated time with them that they'll execute. So for example, all of today's activities were programmed actually weeks in advance and loaded up to the spacecraft. And that is good in that it gives us time to check out all of our sequences. So today, while we're all nervous, there's actually not much we can do except watch the spacecraft go through its series of commands. Now the smaller antenna up there, which is our medium gain antenna, you can tell by the smaller size of it that it has much lower gain than the large antenna. And in fact, it has a data rate less of about a factor of 500. So what would take us 1 minute to download an image on the main antenna would take about 500 minutes on the smaller antenna if we chose to use that. Now the benefit of this smaller antenna is that you don't have to be pointed near as accurately as the high gain antenna. You can point up to 45 degrees off of the bore side of that antenna and still communicate with Earth. So throughout today's activities, we'll be using this medium gain antenna. In fact, right now the spacecraft is pointed in its attitude that it will execute the burn, and we're communicating to Earth through the medium gain antenna. Here you'll see a picture of sort of a large soup can, and we call that the Star Tracker. That Star Tracker was purchased from Ball Aerospace in Colorado, and that's a very complicated and interesting device, and that device is used to actually help orient the spacecraft. Now, how the spacecraft knows where it is it looks through this camera, and the camera takes a picture of it at 5 times a second, and what it does with that picture is it picks out the 5 brightest objects. it gives the location of those objects and the intensity of those objects to a computer on board the spacecraft. Now that computer has a large catalog or dictionary of stars, and their locations and their brightness is relative to each other. And it simply goes through the catalog until it finds a match with a star pattern in the catalog with the star pattern that this camera gives us. And in that way, the spacecraft knows its attitude. The spacecraft does this all autonomously on board. So right now, for example, while the spacecraft is in its burn attitude, this star tracker is looking, it's picking out its 5 brightest stars. The spacecraft then is finding those stars in the catalog and giving the spacecraft the proper attitude. Here you'll see the spacecraft put together, and to give you an approximate size of it, it's about as tall as a man. You can see the propulsion system in the center of the spacecraft. Now, however, those tanks, all those tanks that I showed earlier, are covered with blankets, and those blankets help keep the heat within the spacecraft. Now, where the large thruster is sticking out the side of the spacecraft, you can see that there's an aluminum ring around it. Well, that aluminum ring is simply there to protect that thruster in case someone would accidentally drop a tool on it. Here you can see the spacecraft fully assembled on our shaker table at APL. And what I mean by a shaker table is that the spacecraft is put on that table and it's actually vibrated to simulate the launch environment. And you can see most of the older guys, in fact all the older guys are behind the glass enclosure there. And there's 2 young guys who are out observing the vibration test. The spacecraft, you can see some of the solar arrays there. There are 4 solar arrays. Each solar array is 6 feet by 4 feet. Now you may think that's a large size of a panel, and it actually is. However, right now the spacecraft is out at 1.5 astronomical units from the sun, or about where the orbit of Mars is. So at this distance, these panels really don't provide that much energy. Now each one of these solar panels will produce about 150 watts of energy, and that here 150 watts would be equivalent to the same 150 watt light bulb, say, that you would have at home. So our entire spacecraft throughout this period can consume no more than 600 watts. Now to give you a feeling for that, a standard PC at home, a PC and a terminal at home would consume an order of magnitude more than this. Here you can see some fearless souls standing in front of the spacecraft while the spacecraft is being rotated. It's being rotated about 60 revolutions per minute, and that simulates the environment of the spacecraft while it's on the 3rd stage rocket. Now the 3rd stage rocket spins the spacecraft to stabilize it before the firing of its 3rd stage engine. And if there's any justice to the world, it's that in this actual photo, one of the guys standing close to this spinning mass happens to be our safety engineer. Here you see the spacecraft at Cape Canaveral, and we're testing the spacecraft prior to launch. Here the spacecraft solar panels have been removed, and we're actually simulating the launch environment and the separation from the 3rd stage, and actually the spacecraft flying on its own. And how we do this is all these computers that you see generate signals that actually fake the spacecraft out and produce an environment to simulate actually how the spacecraft will fly and launch. Now you can get sort of a feel of how complicated this is. To test a spacecraft like this, we use electrical engineers, mechanical engineers, physicists, chemists, mechanics. All these talents come together to build and to test the Near spacecraft. Here you can see the Near spacecraft attached to the third stage, actually on the rocket prior to launch. And you can see what we call a clamshell fairing. There's half of the fairing that's actually installed, and this gives you a feel of how the spacecraft actually fits in the top of the rocket. Finally, on February 17th, 1996, and it's hard to believe that that was about 4 years ago, the spacecraft was launched. Since then, the spacecraft is in excellent shape. We have about 5% of our fuel remaining. So if you remember those big propellant tanks, there's just a few kilograms of fuel in each tank. The spacecraft status is that the flight hardware is performing flawlessly. We've had one minor exception in that our backup command transponder on board is suffering a dropout of, say, one command every 100 commands. Fortunately, that's in our backup system, so that doesn't jeopardize the health of the spacecraft. And as I checked in this morning, things are going fine. The spacecraft is in burn attitude, and the commands are loaded on board, and we're simply crossing our fingers, waiting for the commands to execute today. With that, I'll turn it back over to Tom Coughlin.
As has been mentioned many times this morning, our development time was only 26 months. Owing to this short development, we couldn't go through the normal process of selecting scientists, let them bring an instrument with them to the mission. We had to use what we call facility class instruments. That is, APL, the project office, and this project scientist selected a suite of instruments back in December of '93 when we got started, or actually a little before that. And the science team wasn't selected till the following year. Our biggest fear in the development, I know Andy's and I know mine, was here come the scientists, here come the changes. Well, the next fellow I'm going to introduce is Dr. Joe Vaverka from Cornell University. He was one of those scientists, and one of the reasons we did make the 26 months. They all worked together, and we pulled together, and I think it's one of the best examples of engineers and scientists getting along and really all pointing in the same direction. So Joe, with that, and Joe is going to show us some of our most latest images.
Thank you very much, Tom, and as Tom indicated, I'm actually here representing a very large science team, and most specifically the scientists who are involved in the NEAR camera that is taking images and the NEAR spectrometer that is taking spectra of the surface, which is our way of figuring out what kinds of minerals are on the surface. And if you haven't noticed, I am pretty excited, and I hope you're all excited too, because this is a very exciting time. And I hope we also realize that NEAR is really a great spacecraft, because not only in less than an hour, I guess, we're going to go in orbit around Eros, but for the last several months, we have been approaching Eros very, very slowly. And that, let me point out, is very unusual. There have been spacecraft that have flown by asteroids, including NEAR's done this too, but usually at very high speed, 10 or 15 kilometers per second. NEAR right now is approaching the asteroid at about 10 meters per second. That's kind of like sitting in your car driving through the Rocky Mountain National Park with plenty of time to look at everything that you're interested in. And that has been great because, in fact, in the last month and a half, we have so far taken more than 8,000 images of Eros, okay? And I think something like 15,000 spectra of Eros, which again are these things that we use to tell us about the minerals. So it's been a great ride, and it's going to be an even greater mission once we get into orbit. Now, to give you an example of what's been happening, late last night, around 4 o'clock in the morning, we got back from the spacecraft, a very important set of observations. We had spent about a day using our spectrometer to map the surface of Eros under ideal lighting conditions. And this will provide the best map of the minerals that are on the surface of Eros that we will get for many, many months. And most of those data are now safely on the ground, are being analyzed. The analysis is somewhat complicated, so I'm not going to show you a spectrum this morning. But what I will do is show you our currently best image of Eros. And this is an image that was taken just prior to the spectral sequence that I described. And so if we are ready, let's put the best picture of Eros that we have. This picture was taken actually almost 2 days ago. It's the last picture that we have on the ground. And you can see this beautiful asteroid right in front of you. And let me just say a few quick things, because within a few hours, we'll be taking a picture, a series of pictures, which are much, much better than this. And hopefully you'll see one of these before the end of the afternoon. So I don't want to sort of give any explanations right now as to what is in the picture, because this afternoon we'll have a much better one to look at. But clearly, if you look at the picture on the screen, you see a very heavily cratered asteroid. So obviously Eros has been through a history of intense cratering. Some of the prominent sort of larger craters you're looking at are about 2 kilometers across, like 1.2 miles across. The whole object is about 30 kilometers from end to end. So there's plenty of stuff there that will keep us busy, and we have lots of speculations as what will come out this afternoon. But again, let me just say, this is the sort of best picture we have right now to share with you. And very shortly after the burn, we will be taking some much, much better pictures, and one of those you will see this afternoon. Now let me come back to the point I made that over the last month and a half, we have accumulated over 8,000 images of Eros, okay? And what I would like to do is introduce a member of our imaging team, Dr. Scott Murchie of the Applied Physics Laboratory of Johns Hopkins University. And Scott is one of the several individuals who have spent the last several months staying up late at night, working through the whole day, analyzing these data and reducing these data. So I'd like to introduce Scott now to tell us about some of the things that he has been doing for the last month and a half. Scott.
Thank you, Joe. What I'm going to do this morning is take you on a small tour of the last 3 weeks approaching Eros. We'll start out January 22nd and work our way in to where we are this morning on the brink of going into orbit, so that Near will become the first artificial satellite of any asteroid. While we were at a great distance from Eros, one of the things that we looked for was to see whether Eros has any moons or natural satellites. There are 2 asteroids known to have small moons in orbit around them, but we really have very little information on whether this is the usual condition for an asteroid or whether this is very unusual. While we were still 19,000 kilometers from Eros, we had an excellent vantage point from which to examine the space around Eros and look for any small moons. The image mosaic that you're seeing consists of 43 images taken with a very sensitive filter in our imager, using very long exposures to search for any moons or moonlets potentially as small as only 20 meters across, or the size of a small house. And the image mosaic is projected onto the celestial sphere. The way that this is analyzed is that a scientist sits down and identifies all the stars or star-like objects, and one by one matches them against known stars from a star catalog. And the names that you see in blue are some few of the stars that were identified. Eros, still at this great distance, appeared very, very small near the center of the mosaic, labeled in yellow. To date, we have been examining this mosaic and have not yet found any small moons in orbit around Eros. Most of the time, what we have been doing is not looking for moons, but looking at Eros itself. And what you see here is an assembly of some 70 of the best images out of the 8,000 images in the last few weeks. The sequence starts January 22nd, while the spacecraft was still 29,000 kilometers from Eros, and ends on February 12th, when we had approached at that time to a distance of about 2,000 kilometers or 1,200 miles. Now, during this time, Eros first appeared as a small, elongated blotch of light. Daily, it grew larger and larger until by February 7th, we could begin to make out some of the surface features on the asteroid. And if you look midway through the sequence of images, you can see that Eros has details to its shape, a big bite taken out of one side of it, and a small crater on the other side. By a few days later, on February 9th, we got an even better view of Eros than we had gotten during the flyby in December 1998. And at that point, every time images were sent down to the ground daily, we would learn new information about Eros. New features would be discovered, new landmarks on the surface. And you can see in that mosaic that Eros appears to be tumbling end over end out of the distance. And this is because we are approaching Eros in its northern hemisphere with the North Pole on the ground beneath us, and Eros is spinning around and around as we approach it, so we continually view the northern hemisphere in the equatorial region of the asteroid. Now, on February 12th, we took in excess of 900 images of Eros to map the landforms and to measure the color properties of the surface of the asteroid. And I'd like to leave this up for a few minutes and tell you a little bit about the Eros that we have come to know in the last few days. The asteroid is 33 kilometers long, or about 20 miles, 13 kilometers across, or about 8 miles, and its shape can be compared to a peanut, a banana with a bite taken out of it. One side is dominated by a giant gouge about 10 kilometers or 6 miles across, and that is responsible for Eros's characteristic peanut shape. Now, let's continue to look at that image and talk about what we see on the different parts of the asteroid. On the opposite side, there is this very conspicuous crater. That one is 5 kilometers across, and this was the second landmark that we saw on our way in. In the space between and covering the surface of the asteroid, we see a dense population of craters pockmarking the surface. And this tells us that Eros is not a youthful asteroid. It's been exposed to space for some time since its surface was exposed. The way that we know this is that imagine yourself driving in a snowstorm and you turn your windshield wipers off. A snowflake accumulates on the windshield, another one comes in, another one comes in, and you can tell how long your windshield wipers have been off by how much snow you have on the window. It works the same with planetary surfaces. When a surface is old and has been exposed to space for a long time, many meteors and asteroids have impacted the surface and created craters on it. A young surface has relatively few craters, so by looking at the number of craters and their distribution on the surface, we can know that Eros is not as young an asteroid as the youngest asteroid visited by a spacecraft, which is Gaspra. Now, what I'm going to show you next is a movie. Andy mentioned some of the movies that we've been taking, and we've taken a half dozen of these over the last couple of weeks. The one I'm going to show you was taken on February 10th at a range of 3,300 kilometers, or about 1,900 miles from the asteroid. And the way we took the movie is we took one frame every 26 seconds for just over 1 Eros day, which is 5¼ hours long. And as the asteroid rotates, we can watch the surface from different perspectives, watch the lighting conditions change, and being able to observe each spot on the surface over and over under different lighting helps us to understand the shape of the landforms, where the craters are, to separate landforms from brightness markings, and overall to get a much better understanding of Eros as a mini planet than we could from a single still image or a small set of images. So now, as the movie begins, what we'll see is a small description of what it shows. February 10th, 2000. And the interval between the images is 26 seconds. At the speed that this runs, Eros's apparent rotation is speeded up by 780 times. And if you just fix your eyes on one spot on the asteroid, you can see it passing from day to night every 2.5 hours, and the shadowing changing. Right now, the giant gouge is falling into shadow, and the hemisphere with that sharp impact crater is passing through view. Well, could you please continue the movie? The movie actually continues for a number of cycles so that you can get a really good feel for Eros as we know it today. As Joe Vaverka mentioned, these are not the best images that we will have by the end of today. Later today, after insertion into Eros orbit, the spacecraft will turn around and point the cameras at Eros, and from a range of 300 kilometers, we'll snap an image mosaic that will come down to the ground at 12:40, and at 2 o'clock, we will be bringing it over here to show you. And we're just as fast as Domino's Pizza. We'll have it delivery with a smile. So, like I said, this is speeded up by a factor of 780 times, so that what we're watching is one day on Eros repeated over and over again. And I have to tell you, there has been so much planning and so much work that has gone into constructing this. We have a team of over a dozen people who have been working at this since late 1994 now. And this is the culmination of plans that we've had in the works for many years. And there has been a small crew of people at Cornell University, at Northwestern University, here at APL and at JPL, who have become close friends over the years working and planning this mission out in detail. And it's hard to state how happy we are to see ourselves finally going into Eros. And as much fun as we're having now, this is going to be only the beginning. Over the next year, we're going to understand Eros intimately as a planet. We begin in orbit today, 300 kilometers high. By 3 weeks from now, we'll have gotten down to only 200 kilometers, or about 20 miles above the surface, and we'll spend several weeks at that altitude making a complete map of Eros in color, looking at the landforms, creating new movies. And this, for us on the imaging team, is one of the key parts of the mission, because this is our time when we get our best global view of Eros. And then we'll descend down to a 100-kilometer orbit and continue to map at higher and higher resolution. We'll spend the summer at some 50 kilometers, or only about 30 miles above the surface, taking very high resolution views of the surface. And at the end of the mission, we'll be descending down only a few miles off the surface, and we expect to see incredible detail in the surface, features as small as a meter across or less. And this will help us, as Andy Cheng talked about, to get our understanding of Eros as a planet and assemble the information from the variety of instruments that will help us to gather all the information from Eros and assemble the clues and learn what it tells us about the origin of the Earth and the inner planets. Thank you. And now I'll hand things back to you, Tom.